Morning, students. Today we discuss FET amplifiers. Now, FET you have learned in your the construction of a FET, its working principle, its characteristics, etc., etc., etc. You have learned in your device classes in earlier semester, like in your BJT. So I'm not going to repeat the construction and working principle of a FET, right? So today we are straight going to FET amplifiers. Now, while discussing FET amplifiers, still a few salient points, one or two of a FET we need to recollect. One is here, you have it in front of you, the salient points of a FET, like BJTs are current control devices. BJT's collector current IC is proportional to beta multiplied by its base current. So BJT is a current control device. Its collector current is proportional to base current. Whereas in FET, it is drain current is proportional to base gate voltage. That's why FETs are called voltage control devices. And with this equation in a BJT, when you apply a varying signal current in the base, it produces a varies collector current, and that varying collector current flowing through the load produces a varying output voltage. In case of a FET, the varying volt potential at the gate produces a varying drain current. And because of this, there are some advantages of a FET over a BJT amplifier. And what are those advantages? We shall see one by one. Second point, input resistance of a BJT is low because BJT base emitter is just like a diode junction. Its inherent resistance is only HIE or a diode resistance, which is of the order of at 1 milliampere current, it is about 25 ohm. And so altogether, this input resistance is something like between around 50 ohm or even less than that. Whereas FET being a source device, the current flowing into the gate source junction is nil, zero. So the input impedance of a FET is very, very high. And that is why a FET amplifier is preferred when you want input impedance to be high. Next point is a circumstantial point. Neither FET is at fault, neither BJT. BJTs have only two varieties, NPN and PNP. So it is easier for students to remember. Whereas FET has many varieties. It has got JFET, it has got MOSFET. In JFET, it has got P-channel, NPN, P-channel, N-channel. In MOSFET also, there are enhancement MOSFET, depletion MOSFETs, each having N-channel, P-channel. Then there are CMOS. So there are so many varieties. The students at their early life often get confused with the FET. But I have a clue to get out of this conclusion. I'll come to that later. Another point of a FET amplifier, FET amplifiers are much easier to design in BJT amplifier, because BJT amplifier, the few 6-7 basic components, the performance or the effect of one component depends on the effect of another component. But in FET, it is not so. First point, FET amplifiers have very low gain, voltage gain, whereas BJT amplifiers have high gain. So if you want a signal to be amplified, then BJT is better than FET. Then the question comes, why FET amplifiers are required at all? We shall reply those questions one by one. This is a common source FET amplifier. The purpose of various components are exactly same as those on common BJT amplifier. I think you have already noted that this looks exactly like a BJT amplifier, except instead of BJT, it's a FET here. Amplifier, there is a collector current here, there is the drain resistance. In BJT, there is a emitter resistance, it's a source resistance. In BJT, there is a emitter bypass capacitor, it is a source bypass capacitor. In BJT, there is a coupling capacitor, input coupling capacitor, output. The same thing is here. In BJT, there is a load resistance. In BJT, of course, there will be a source to supply to the BJT amplifier. In BJT amplifier, also there is a self-biasing R1, R2, and FET also there is same self-biasing R1, R2. Then what is the difference? Can we convert a BJT amplifier into a FET amplifier just by replacing the BJT by a FET or vice versa? Answer is, of course, no. Answer is no. Because the biasing technique in a FET is different. In BJT, current flows into this input circuit, but in FET, no current flows through this. Only a potential is created here. So the biasing technique has to be different. We shall see what is the difference. Firstly, as I said, I'll give you a guideline. Take a N-channel JFET because there are so many FETs. Which one you should take? I say this is the easiest and simplest one and the sturdiest one. That means it is, you cannot damage a JFET so easily. But a MOSFET, a little bit of mishandling or a hit in soldering the MOSFET leads will damage the MOSFET itself. So use a JFET and use a N-channel JFET because if it is an N-channel, then you give a positive 10 volt here or some 15 volt, whatever voltage. And also, JFET, I propose BFW10, which is very low cost FET and easily available in your college laboratory. This is the first step. Select the FET. Second step, go to the data manual of the FET. Nowadays, such data manuals you can get in Google search also. Data manual says for BFW10, maximum value of IDS, drain source current here, is 10 milliampere and maximum drain source voltage here, that means voltage across these two terminals, is 30 volt. Right? Also find out this characteristic, drain characteristics from the data manual, and sometimes you can get it in Google search also. Characteristics, etc. you have learned in your device classes. The y-axis is the drain current, this current. X-axis is this drain source voltage, this voltage. And these are the various curves which are for various values of VGS. That means voltage from here to here, not from here to ground. Mind it. Many students make this mistake. It is this voltage from terminal to terminal, gate to source. And for green curve is for 0 volt. And as you go negative, since it's an N-channel FET, this will be negative. So as you go negative, the drain current goes on reducing. Right? The curve looks similar to output characteristics of a transistor, but in FET, these characteristics are more flat, but in transistor, these characteristics are like this. It is more slope. So I repeat, first select the FET, then find out its maximum currents and voltages given, then find out its characteristic curve. Then maximum values of this current and voltage is given. You decide yourself, for safety of yourself and for the FET, a lower value. Maximum current is given 10 milliampere. I have decided I will not go up above 8 milliampere. Maximum voltage here is 30 volt. I have decided to limit myself in 10 volt because 10-volt power supplies are easily available in college laboratories. So I draw this card between 8-volt and 10-volt, right? Sorry, 8 milliampere current and 10-volt VGS. Next step, what is the DC load line here? Is VDD is equal to ID into RD plus RS. These are the two resistances in this line, plus this potential drop VDS. So this is a straight line, and this straight line is this straight line, right? Now, at VDS to at 0, IDS is maximum. And we have already decided maximum IDS is 8 milliampere. So in this equation, when this is 0, this is 8 milliampere, and this is selected to be 10 volt. So what is RD plus RS? Is 1.25K. So these two are 1.25K. These two together is 1.25K. Now you remember I suggested you in BJT amplifier design that the ratio of these two should be around 1:5. This is a thumb rule. And also I explained in various places that why this ratio is good. In FET also, I always propose this ratio, not 1:5, not so high ratio, say around 1:3 or something like that. So this 1.25K, I divide in two parts. I make this RD as 1K and RS as 0.25K. So it is once again 1:4 ratio. So see, these two resistances are already decided. So half of your design is complete. Next, I have to decide only these two resistances. Approach line is there. This is the DC load line, 8 milliampere maximum, 10 millivolt, 10 volt maximum. Now look at the DC load line. Here, my operating point will operate on this. I do not want to go above points because these are the nonlinear region of the characteristic curve. Also, I do not want to go too low because if I go too low, then if signal is little higher, the one end of the signal output will be cut off or clipped. So I want to remain, say, from here to this point. From this point to this point. If you take this area, then you find out from graphically what is the midpoint of this load line. With a scale or a graph paper, if you have midpoint of a load line, what I have found, you will find maybe at a different value, is VG IDSQ, this current here on the y-axis at the midpoint is 3.5 milliamp. And this is neither on the blue line nor on this yellow line. It is somewhere in between here, graphically I found. So it is 0.5 volt line, minus 0.5 volt line, it is minus 0.75 volt line. So I consider to be at 0.6, minus 0.6 volt line. So two more decisions have been taken. That quiescent drain current will be 3.5 milliampere and quiescent gate source voltage will be minus 0.6 volt. Mind it, this is not VGG. VGG is gate to common. Gate source is gate to source terminal. Right? From VGG, we can find out R1, R2. How? See, if drain current, quiescent drain current is 3.5 milliampere, it flows through RS. RS value is 0.25K. So what is the potential here? 2.5 milliampere, 3.5 milliampere into 0.25K is 0.875 volt. So you have here 0.875 volt. And this point should be 0.6 volt less. So VGGQ should be 0.875 minus zero point 0.6 is equal to 0.275 volt. This point I want at 0.275 volt. Now to get 0.275 volt, as a guideline, I propose you take R2 to be 2K. I do not insist on that, but I will show you the calculation. You take R2 2K. If you take R2 2K, then what happens? Then 10 volt divided by R1 plus 2K equal to 0.275 volt you want, you get R1 equal to 71K. So if you take any value, other value is available. Now, your question is, what is the guideline to take 2K? Guideline is, what is the source, what is the impedance seen by the source is R1 and R2 in parallel. So these two in parallel, 2K and 21K in parallel, will be slightly less than 2K. So input impedance seen by the source is 2K. If you want it much higher, you multiply it by 10, multiply this also by 10. You take 20K, it is 710K. Then input impedance seen by the source will be around 20K, a little less than 20K. So you have to maintain this ratio and see what input impedance you want. Now the point is, the FET amplifiers are used for their high impedance. So you can go take higher values. Why 2K? You can make 2 mega. Then input impedance to this amplifier will be around 2 mega, which is very good for this source. Right? For this source. Also, there is another issue. When these values are higher, there is much less current flows through this line. This current flowing through this bias line does not contribute anywhere in signal amplification. Now, if you are in your laboratory, then you have a power supply. You don't bother about the DC current. But if it is a small electronics, like an electronic wristwatch or something like this, where current consumption is very, very important, there you take high values. So DC current consumption is very low. So these are the considerations. So these are the values we got. Just 4 values: RD, RS, R1, R2. 1K, 0.25K, 2K, 71K. Our design is complete. And our design basis is gate source voltage is minus 0.6 volt and drain current, quiescent current is 3.5 milliampere. With this now, we can check this amplifier. Let's check. I'll switch over the screen for a second, so then it will be an interruption. Don't bother about the interruption. Just wait. So I have come to the testing software. I have used the same 1K, 250 ohm, 71K, 2K, all these values are same, right? And the circuit looks like a BJT amplifier only, except it is a FET. Let's see how it works. Let's switch on the oscilloscope and run it. See, I get clear waveform. The blue one is the input and the red one is the output. Both scales here are same. So you see gain is not very high. As I told you at the beginning, FET amplifier gain is not very high, right? To measure the gain, I take a voltage probe here, another voltage probe here, and run once again. The output peak-to-peak voltage is 2.88 volt. Input peak-to-peak voltage is 848 millivolt. That makes the voltage gain to be around 3.36. So you may be deserted that gain is so low. Because in a BGT amplifier, even if you are a careless designer, you get a gain of 50. So FET amplifier is not purpose is not FET amplifier purpose is not amplification. FET amplifier purpose is to provide high input impedance and some other aspects. I'm coming to that, right? I'm coming to that. So gain is very low. Next is I'll switch off the oscilloscope. Let us see the distortion and the frequency plot also. This and I find distortion is only 4.5%. This is excellent because in a BGT amplifier, getting distortion less than 15% or 10% is very difficult. Why? The answer is in a BJT, current flows through the base emitter junction, and base emitter junction characteristics is nonlinear. Remember, base emitter junction of a transistor is a PN junction diode, like a diode, but it's a PN junction, and characteristics is always nonlinear. Whereas in FET, no current flows through this. No current flows through this. So that nonlinearity due to the signal current input is not there. A little bit of nonlinearity is there in a FET that is due to some nonlinearity in the drain characteristics. So this is one major benefit. Second major benefit is its characteristics. See, its midband gain is 10.711. Let us forget of the upper band. It is very, very high. So if we go find out the lower frequency, 10.711 minus 3 is 7.711. 7 point, right, like this. It is only 19.3 hertz, like something like 20 hertz. So it has a very good low frequency gain. Whereas in a BJT, low frequency cutoff will be always something like 100 hertz or above. That also is a good design practice. So now you know the benefits of FET amplifier. It's low frequency. That means if you have an audio signal which has a lot of bus frequency, then is a FET amplifier is good. And it has got very high input impedance. So normally in a cascaded audio amplifier, the first stage is a FET amplifier, or the first stage is also called pre-amplifier stage. Pre-amplifier stage is a FET amplifier because the pre-amplifier stage decides the equalizing characteristics and distortion, etc. of an amplifier, where you use a FET amplifier, which gives a very accurate distortionless amplification, but amplification ratio is small. And after this pre-amplifier, you may use transistor amplifiers so that the power is enhanced. So this is how a FET amplifier works. And you have also seen with this design, our drain source current quiescent point design value was 3.5 milliamps. We got is 3.527 milliamps, which is very good. And our gate source voltage design was minus 0.6 volt. We got minus 0.607 volt. So I think I could establish to you that there is nothing to be afraid of. Just follow the steps given one by one. You will always get a good amplifier. So here we finish the chapter of common source amplifier. In our next lesson, we shall discuss common gate and common drain amplifiers. Okay. Lastly, let me give a request to you that if you are in a good mood, please subscribe to the channel so that I get some